Bueno, lo primero de todo, agradecer la presentación. Thank you very much for the presentation. So today I'm going to talk about the recent paper that we published last year, the PNG-UNITsims project. First of all, I would like also to thank the RES and the BSc for allowing us to access Mare Nostrum 4 machine. Without this access, this project wouldn't have been possible. And then I will structure the talk in these three parts. First, I want to make a broad introduction to what is cosmology, to what is primordial non-Gaussianity, which is the key topic of this paper, how these simulations are performed, what is the importance. Then I will talk about how we perform these cosmological embodied simulations using the resources from the RES. And then I will talk about the proper project that we perform for this paper. So first of all, I would like to introduce what is cosmology. So cosmology is the science, or is the branch of the physics which is in charge of studying qualitatively or quantitatively the origin, the composition, and the evolution of the universe as a whole, not as the individual particles. And it's based on two basic pillars. The first of one is the general relativity, which provides us with a framework to describe how gravity works in all the scales. In broad words, we can say that general relativity matter tells how the space-time has to curve, and the curvature of the space-time tells the matter how to move. And the second basic pillar of cosmology, and modern cosmology, is the so-called cosmological principle. This states that on very large scales, on sufficiently large scales, the universe is both homogeneous and isotropic. At every point, the universe has the same properties, and if we look at every direction, it has the same appearance. Of course, this is not true at total scales, because otherwise, the stars, the galaxies, the planets, and ultimately us couldn't have form. This is only when we average over large scales. The consequence of these two principles is that we only need 6 free parameters to describe, from the distribution of galaxies, the growth of a structure in the early universe, down to the small temperature perturbations that we observe today in the cosmic microwave background, with only 6 parameters. This concordance model, often called lambda CDM model, is based on two unknowns for the physicists or for the community, which is called, this lambda is the dark energy. This component that we don't know much about it is the responsible of the expansion of the universe. And it accounts for the 70% of the total energy content of the universe. The second component that we need for describe this model is the so-called cold dark matter, or CDM, right? Which accounts for the 25% of the total energy content of the universe. This dark matter only interacts with the ordinary matter through the gravitational interaction. No other interaction are allowed, so we cannot observe it directly. We have a lot of evidence of its presence, but we cannot know yet its nature, and we cannot observe directly. And the rest, all the ordinary matter that we can see surrounding us, that we can see through telescopes in form of gas, stars, galaxies, planets, everything is only the 5% of the total energy budget, or matter energy budget of the universe, right? And one key observation that for the last decade in cosmology is the realization that if we look at the galaxies that surround us, most of them are receding from us. So, and even more, if we look farther, they are receding even farther. The explanation to this observation is that not is the peculiar motion of these galaxies, but rather is the space itself which is expanding. And the logical consequence of this expansion of the universe is that if we go to the past, the universe has to be smaller. And if we go farther and farther to the past, this universe has to be very, very, very small and even much, much hotter. So the hot Big Bang model is very powerful because together with our knowledge of the nuclear physics and so allow us to predict some quantities such as the abundances of light elements such as hydrogen and helium that we find in the universe, and also the temperature, the cosmic microwave background that we can observe when we point our telescopes in every direction. But this hot Big Bang model requires for extremely fine-tuned initial conditions. Basically, if we draw a triangle between galaxies, we realize that the sum of the internal angles are 180 degrees. This means that the universe is extremely flat. The only deviation that we can constrain is 1 part into 1,000. But this is today. So if today the universe is so flat, if we go to the past, to the origin of the universe has to be extremely flatter. The deviation has to be 1 part in 10 to the 60 power, right? So, and there is no theoretical motivation for this value to be like that. So this is like a very common problem known as the flatness problem of the Big Bang. There are also some others. So how can we circumvent this problem? So we can invoke this inflationary paradigm, which is a set of theories that said that just after the beginning of the universe experienced a period of exponential expansion, just from 10 to the minus 35 seconds to 10 to the minus 13 seconds. The universe expanding from the size of a proton out to a size which is larger than the solar system today, right? In just this tiny fraction of a second. This helps us in order to solve this flatness problem, because all initial perturbation in the initial curvature that the universe might have is completely smoothed out after this period. And what can produce this? So in the simplest scenario, we have a quantum field, which is often called in the literature as inflaton, which causes this period of exponential expansion. And also this came with a bonus, because this quantum field suffers from quantum fluctuation due to the Heisenberg uncertainty principle, and these tiny fluctuations, which are of a quantum size, get amplified to macroscopic scale. These perturbations in the density field later will develop or will serve as a seed for the origin of structures such as galaxies, galaxy clusters, and ultimately the large-scale structure of the universe. And then I want to comment briefly about this primordial non-Gaussianity. The standard model for inflation just requires from a single field, the inflaton. So these quantum fluctuations have an amplitude which follow a Gaussian distribution, which is symmetric in both high density and low density perturbations. However, more complex physics, if you have different fields or you have non-canonical kinetic terms or whatever, basically if you have different physics, you usually generate deviation from this Gaussianity. One of the most popular models is so-called the local primordial non-Gaussianity, which usually arises when you have at least 2 fields during inflation. And then you have this, there's the curvature perturbation, this phi g, right? And it's modified with this FNL, is the amplitude of these non-Gaussianities, phi squared. So it's now, the PDF is no longer a Gaussian, but it acquires a skewness toward, in this case, positive values. But if we change the sign, we have the skewness in the opposite direction. So if we are able to measure this kind of effects, we can say a lot of things about the physics that were occurring just at the beginning of the universe. This is the interest that we have on this primordial non-Gaussianity. And one of the most promising ways of constraining this primordial non-Gaussianity is through the so-called large-scale structure of the universe. Now, in these days, there are 2 very big experiments, such as DESI and Euclid, which are mapping the distribution of tens of millions of galaxies around the sky. This, for example, is the first year of data from the DESI collaboration, and every single dot that you see in that image is a different galaxy, right? And this distribution of galaxies allow us to prove a bunch of different physics processes, from how a structure grows in time in the universe, through up to the nature of gravity, and of course, the initial condition of the universe and this primordial non-Gaussianity. So the tool that we use in cosmology, or the most popular tool that we use in cosmology to extract information from this distribution, is the so-called 2-point correlation function that we can see in this animation. Is just counting how many pairs of galaxies are given for a certain distance, right? And this is the shape that we measure in the 2-point correlation function. But also it's very common to work with the power spectrum, that is the Fourier counterpart of this 2-point correlation function. Now let me introduce another concept, which is the concept of galaxy bias. The idea is that we do not have access to the direct matter distribution. As we said, the 25% of the energy content is the dark matter that we cannot observe directly with telescopes, and we can only observe the 5% of the ordinary matter through light, galaxies, etc. Here I have an analogy of the Iberian Peninsula, right, during the night. So you cannot directly observe where the ground is in this image, right? But you can see the cities or the city lights. So these city lights always form on top of the ground, but so in every place that you see a city, you can infer that there is ground, but not in every place that there is no city, there is no ground, right? So in that sense, the city are a biased tracer of the underlying ground of the Iberian Peninsula, right? And the same happens with galaxies. We do not observe the total matter distribution, but we observe the galaxy distribution. So at the level of the power spectrum that I previously mentioned, this blue line is what we would measure if we have access to the total matter distribution, and this orange line is what we could measure, or what we actually measure, when using the power spectrum of the galaxy distribution. So the key thing is that in presence of primordial non-Gaussianity, this bias relation, that is the first expression that I have given you, is now modified. You have a new term which is proportional to FNL, the amplitude of these primordial non-Gaussianities. B phi is how galaxies respond to the presence of these primordial non-Gaussianities, and this alpha k, which encodes some physical effects, right? At the level of the power spectrum, how does this translate? So instead of measuring the orange line, we would expect to measure the green line. Okay, but here there is a very important problem, right? Because if you see in this expression, you find that B phi is always multiplying FNL. If we are not able to fix one of those, we cannot extract the other. Because always I can come up with a different combination of B phi or FNL values that gives the same signal. Okay, so for example, I overplotted a different set of B phi and FNL, which produce the same signal as the original green line, right? So we need to know what this B phi is, or usually parameterized in terms of this value P, if we want ever to measure FNL from these galaxy surveys, right? And here is where simulations come into play. Now there is a debate in the community what B phi should we use for the galaxies that we are observing in DESI and Euclid, and it's not clear. The idea is that we can perform numerical simulations or cosmological simulations in order to extract a value of B phi, physically motivated, based on our assumptions, in order to use this value of B phi to analyze the data. And finally, we may be able to say things about inflation. So how do we simulate the universe? So let's break the problem. The first thing that we have to take into account is that the universe is expanding. So we have to simulate this expansion of the universe, and this is captured by the so-called Friedman equations. These Friedman equations are quite easy to solve, and even there exist some analytical solutions for many of these problems. So that is the easy part. The next part that we have to solve or simulate is gravity. Okay? So in order to simulate how a distribution of matter evolves with gravity, we have to solve the so-called Boltzmann-Einstein system, which is a system of 6 + 1 dimensional system of equations. The message is that this is super hard. Unless we have a very simplified assumptions, we cannot solve this analytically. But this is not all the film, right? We have many more physics that we would like to simulate in order to produce a copy of the universe in our computers, right? We have to include the stellar formation, gas physics, black hole physics, supernova, winds, shocks. This is incredibly hard to simulate. But as I said previously, this baryonic or this ordinary matter just account for the 5%. The other 95% is the dark matter and the dark energy, which is included in these two terms. So as a first approximation, that what is usually done is just neglect the other part and just focus on the so-called gravity-only or dark matter-only simulations. In this case, the simulation or the dynamics of the dark matter distribution under the gravity and the expansion of the universe is simplified in some sense to what is called the Blasov-Poisson system, which are these two equations. The first equation, this F, is basically the distribution of the matter. And basically, this equation tells you how this distribution evolves through time. And it's coupled to the Poisson equation, which basically tells you how gravity works, right? However, this is still too complex, and we cannot solve this problem unless very specific conditions in an exact manner. So we have to resort to numerical methods. So let's say that our matter distribution is that gray line. The idea that we have in order to solve this is to use some tracers or particles that we will use to describe this matter distribution. The larger the number of particles that you use, the closer this system will follow the continuum limit, right? This is the embody technique. And then, under these assumptions, these very complex equations, the first one, just reduce to these two equations that we have for every particle. So basically, the position of a particle in a step I plus 1 is the position that it has in the previous step, plus its velocity times the delta time between these two time steps. And the velocity gets updated in a similar way. So the velocity is the velocity in the previous step plus the acceleration, which is basically the force given by the gravity, plus delta time. So what are the things that we need to perform a cosmological simulation? The very first step is to set up the cosmology, the parameters that we want to insert in our model. And from that, using linear theory, which is a set of very complicated equations, we can generate the initial perturbations, the initial conditions for our simulation, right? This is the initial perturbations from the inflationary model that you want to have. If you have primordial non-Gaussianity, once you have this initial perturbation, you just add FNL times that field square, right? Then, what we have to specify is the initial condition for the embodied problem. As I said, we have the rule to update the particle positions and the particle velocities, just adding the velocity and the force, the gravity force. So we need to specify the initial position and the initial velocity. This is done typically with a technique which is called perturbation theory, given the field that we generated in the previous step. Next, the most expensive part is the embodied evolution. Now we have a bunch of particles with initial velocities and positions, and we have to keep track of the evolution from the point that you start your simulation until today, right? This typically consumes a lot of CPU time and a lot of resources in order to do this embodied evolution. And the final step is post-processing the outputs of this simulation, right? Up to now, the output that you have from this embodied simulation is the dark matter or the matter distribution of the universe. So the problem that you have is how to connect these outputs with the actual observations that you do for the galaxies. There are many techniques, so you can find the clamps in the matter distribution from your simulation and assign these clamps to galaxies with different techniques. Then you can imprint some realism of trying to mimic how these galaxy surveys actually work. For example, you can put the footprint of this survey, etc. And you can put a bunch of observational systematics, right? And in this context, we perform the PNG unit simulation. This is what we do for this specific paper. The unit simulation, the PNG unit simulation, is actually one of the largest simulations to date that include these primordial non-Gaussianities. It has a number of particles of 400,000 to the cube particles, which is roughly 7 times 10 to the power of 10 particles. Is huge. And the size is 1 gigaparsec size. The FNL value that we said is FNL 100, and it actually consumed like roughly slightly more than 1 million CPU hours in Mare Nostrum 4, right? What you see at the right is the slice of the dark matter distribution of this unit simulation. This is the full size is a 1 gigaparsec. Then you see one zooming around the 250 megaparsec zooming, and the last one is the zooming around the most massive halo of 20 megaparsec. To put this a bit into context, the original resolution of the zooming around the most massive halo, right, has 4,000 pixels. So to put it into context, our galaxy will be of the size of 2 pixels in that image, right? So now put it into the very large box in order to have a sense on how big is this simulation. And currently, apart from the result that I'm going to present in the next few slides, this simulation is being used in the DESI collaboration and in Euclid collaboration to try to find out what this B phi, or this value of P, is for the galaxies that these collaborations will use to measure these primordial non-Gaussianities from the real observations. They are using for validating how the pipelines work in order to extract this information from the observation. They are using this simulation to assess the impact of observational systematics, like the fact that you are not observing the full sky, just a small part, etc. How all of this impact to the measurement of FNL. Because in this simulation, you know that the value that you should extract at the end is 100, right? So now I'm going to talk about a bit more technical about the results of this paper. So our idea is to measure what is the value of this P for the halos, the clumps of the dark matter that we found in our simulation. So the idea is that we are using this effect, the scale-dependent bias, where we are only measuring, or the quantity that, in fact, we are sensitive to is B phi times FNL, right? So this is what, in this figure, I'm showing in orange dots. Apart from this simulation, from some years ago, our collaborators developed a Gaussian version with FNL equal to 0 of this simulation. So basically, we have two simulations which simulate the same parts of the universe, but one with one cosmology with FNL 100 and the other one with FNL 0. So the Gaussian one is shown as blue dots. So in case of FNL 0, all the dots should lie exactly in the 0 line, right? So as long as this measurement has some noise, we can use this correlation between these two simulations to reduce the errors that we have in our measurement in the non-Gaussian simulation, right? And this is what I'm showing in the green dots. So given we know this value, what we can do next is to derive, we know FNL, we can solve for B phi, and we can derive what is the value of P, right? This is what I am showing in this right panel. So basically, there are some theoretical predictions for dark matter halos that this value should be exactly 1. But what we find is that for different masses, there are some fluctuations, and overall, the best fit for all the masses at once is these pink areas, which is this value of P, which is slightly less than 1. So this technique that we have applied for dark matter halos, the idea is to apply to the actual galaxies that we can find in this simulation and use that value in order to extract FNL from real observations. So the idea is we need to fix P to extract FNL. This is the message that I want you to take. And because if we assume a wrong P, for example, P equal to 1, and it turns to be that it's not the real one, this can induce systematic biases in the measurement of FNL, and so in the conclusion that you have about inflation. So it's very important to know exactly the correct value of P. And using the size of the errors that we get from our simulation, we can get constraints which are comparable to fixing P to the fiducial value at the time that you avoid any bias because you are using the correct one, right? This is described in this figure. So the larger the uncertainty that you have in P, the larger the uncertainty that you get in FNL because of this effect that they are both degenerated. If you fix P with a very small error, right, you get a minimum error in FNL, which is due to the cosmic variance. And this vertical line is what we get, is the size of error that we get from our simulation. And basically, the idea is that it's capable of breaking this degeneracy at the same time that you can get unbiased measurements of FNL. And then I want to finish my presentation with some bullet points. So the idea is that cosmological simulations are very powerful tool for cosmologists in order that we can test all variations of analysis in a controlled environment where we know exactly what we should recover. We developed one of the largest simulations up to date with local primordial non-Gaussianity, the PNG-UNITsims, and it's publicly available at the moment in the UNITsim, and very soon also at the peak. We measure the value of P as a function of the halo mass, and we find that it's better described by this P equal to 0.95 instead of the expectation value of P equal to 1. And this simulation is currently being used for the cosmology community for a variety of projects. For P for desi galaxies using different semi-analytic models, P for merger history using the merger history of the halos, etc. So thank you very much, and I'm happy to answer your questions.